a day made 24 little hours, bought the sun and the flowers where there used to be rain. My yesterday was blue, dear. Today I'm a part of you, dear. My lonely nights are through, dear, since you said you were mine. Lord, what a difference a day makes. There's a rainbow before me, skies above can't be stormy. Since that moment of bliss, that thrilling kiss, it's heaven when you find romance on your menu. What a difference a day made, and the difference is you.
If you ever go down Trinidad, they make you feel so very glad. Calypso sing and make up rhyme, guarantee you one real good fine time. Drinking rum and Coca-Cola, go down Point Cumana, both mother and daughter, working for the Yankee dollar. Oh, beat it, man, beat it. Since the Yankee come to Trinidad, they got the young girls all going mad. Young girls say they treat 'em nice, make Trinidad like paradise. Drinking rum and Coca-Cola, go down Point Cumana, both mother and daughter, working for the Yankee dollar. Oh, you vex me, you vex me. From Chickachickarry to Mona's Isle, native girls all dance and smile. Help soldier celebrate his leave, make every day like New Year's Eve. Drinking rum and Coca-Cola, go down Point Cumana, both mother and daughter, working for the Yankee dollar. It's a fact, man, it's a fact. In old Trinidad I also fear the situation is mighty queer. Like the Yankee girl, the native swoon when she heard her bingle croon. Drinking rum and Coca-Cola, go down Point Cumana, both mother and daughter, working for the Yankee dollar. Out on Manzanella Beach, GI romance with native peach. All night long make tropic love, next day sit in hot sun and cool off. Drinking rum and Coca-Cola, go down Point Cumana, both mother and daughter, working for the Yankee dollar. It's a fact, man.
Good morning, guys. It's been a while since I've done this. Hopefully, this is going to be working fine. I think I actually sent a message invitation to everyone, so you should have the link. Can you just give me a thumbs up in the chat to make sure that everybody's there and well, at least that you're hearing me. I think it's broadcasting. It should be all okay. All right. So, the storm, the return of the vengeance. Okay, thumbs up. So it seems like this is working. So today we are entering the last two lectures on mixed integer programming. It shouldn't be too bad. Hopefully it will work all right. If you have questions, please put them in the chat here on YouTube so that I can actually see your questions and respond. I know that there is like a 5-second delay at least between the live stream and me speaking. So be patient if there is a little bit of delay for me answering question. With that being said, let's get going. So what we have to do is the following. We are going today to be discussing, ta-da, polyhedral cuts. I already hinted at those in class, right? This is an important topic. Because these are the kind of cuts that are going to actually chop off our polyhedron so that the facets become adjacent to integer vertices. And it has the positive effect that, of course, once you do that, it's much easier to actually use the linear programming solver. The simplex will immediately zero in on integer solutions if the vertices have integer coordinates. So that's the whole point. That's what we're going to look at today and the next lecture as well. All right, good. So you remember that triangle? This was from last time. We had a system with two inequalities. x1 and x2 had to be positive. And then I had two inequalities, one on this side and one on the other. And the solution was fractional. And we used Gomori cuts to slice off the top here and then take a sideways cut here and settle on the vertex. So this was a syntactic cut, not a polyhedral cut. It didn't actually settle down on our integer solution. Just as a reminder, I think that it's good to take a look at that guy and remember that those dots that you now see, right? So this guy up here, the one down there, here and here, are the only integral points inside the polytope. Because they are, what I'm really interested in is this smaller polyhedron, right? This one has, as you notice, integer coordinates for its vertices. If I had inequalities that were defining the sides of this dark gray polyhedron, I would be exactly on integer solution when the LP solves. It would directly settle on the 1-1 solution with the maximum and we'd be done. No need to generate cuts, no need to branch. Life would be actually totally outstanding. And this is something that happens quite often. So let's take a look at a few other situations. Here's a bigger one, still in 2D. We've seen that one, that polyhedron in the past, or that polytope, I should say. We typically, by the way, we typically say polygon when it's not even convex, polytope when it's convex, polyhedron when it's convex and has integer coordinates. And this guy clearly doesn't have integer coordinates, so this is a polytope, strictly speaking. And if I'm minimizing or maximizing, you know I will end up on the surface and I will have a fractional solution. In reality, though, the point that I'm interested in are the ones that you see now. These guys all of them sit on integer coordinate. That's what I really care about. And you notice that, yes, well, that's not exactly the one that we get on the edge, right? So this is a little further off. This is a little further off. This guy happens to be on the edge, but that's pretty much one of the rare ones. The other guys are a little way out. So what we really want is this shape instead, right? That's a polyhedron because it has integer coordinates for its vertices. If I had a precise characterization, you would directly see that the LP, when it optimized my objective function, would land on a vertex that's optimal and has integer coordinates. And life would be perfect. One thing that may be worth noticing, and feel free to comment on this, but I think that it's pretty obvious if you look, for example, at the orange half plane here. I have a single half plane, and look at how many facets are close by on the integer polyhedron. There are two of them where I had one facet here. Even on this guy, on the purple one, I had only one, but here there are 1 and 2 here. Like, look at the long red one. There is 1, 2, 3, 4 of them. So as you try to get a crisper polyhedron that just encapsulate exactly the integral point, you see what's happening is that the number of facets is going to increase, substantially so. So the equations that you would typically write, the colored ones, they're fewer, but they're not tight. If you want something tight, typically you would need a lot more specification to actually catch these facets on the sides of your polyhedron. And that's where the devil lies, right? That's where the difficulty will show up. So we're going to take a look at this guy and try to see, like, what can we do with it. Just in case you're not convinced that there are a lot, in 3D, remember, we've seen those pictures, and of course, there are integer points inside. And if you try to get something that's a little tighter, yeah, sure, it becomes more delicate. You have a lot more facets as you do this game, right? So this is the basic idea. So back on this one, I'm going to try and get the vertices of interest. What I'm talking about is getting polyhedral cut. So unlike Gomori, which are syntactic and are not guaranteed to give us something that is tangent to integer vertices, the polyhedral cut are meant to represent facets of the convex hull of integer solution, which is the dark gray you see inside, right? This is the convex hull of integer solution. That is, all the integer solutions are inside on the surface of it. That's what I want. And I'd like to go from the colored half planes that are the one from the linear programming model to see, can we tighten this thing and get facets that have integer coordinates for the points inside of it. And that's the main thing. If I can generate this, it would be wonderful because the LP gives me a solution, and they have to verify some properties, just like our Gomori cuts. First and foremost, they cannot remove any solutions, right? Nothing has changed on that front. I need to make sure that all my solutions remain unmolested as I add these cuts. Second thing is that they should be as strong as possible. You clearly see that if you had all of them, you give this whole collection to the LP solves your problem, you walk away laughing, no difficulty whatsoever. That, of course, is not always going to be that straightforward. So my polyhedral cuts, how am I going to get them? The idea is to exploit the problem structure. So far, the Gomori cuts were blindly looking at the tableau without any understanding of what the inequalities meant. They were just a collection of half planes whose intersection defined our polytope. Now we're going to say, no, these half planes, they have meaning. They have semantics. I can look at my problem and see where it comes from. And if I understand the semantics of the inequalities, maybe, just maybe, I can get a better, stronger characterization that exploits the meaning of the problem to actually give me that, right? So this is the main point. Of course, what they share with the Gomori cut is the spirit. They must be valid. They cannot cut an optimal feasible solution that's integral. And they must cut the current basic feasible solution. So if you have a BFS, which is fractional, they need to cut it. Exactly like Gomori cuts, there is no way around this. They need to cut the BFS. So we're going to keep this primal dual technique that we have covered so far. But I'd like them to be valid and not cut an integer solution. Otherwise, I run the risk of missing my optimum, right? So this is the basic thing. Just like for Gomori cuts, you do not need to generate them all, right? I said, yes, in a perfect world, if you had all of them, you could just let the LP loose on that and you'd get the solution. But generating all of them may be prohibitive. So what we're going to need to do is just generate them selectively, generate just a subset, because it will be much more manageable inside. And I'd like to generate the subset that is relevant at any one point in time. That is, I'd like to generate the subset that is close to a BFS that I do not like. That is a BFS that's fractional, right? So it's the same kind of ideas as Gomori, but now I want to generate something that's structured. Of course, the kind of structure is going to depend on the problem. There will be a bunch of them. We're going to look at a handful, not all. There are typically hundreds of cuts like that are semantic, but we'll look at a handful of them to try and get a good bearing on what's going on. So before going any further, any questions on the motivation, on what we've done so far? If you guys are good, just give me one thumbs up or anything. I know that we're okay. Yes, no, anybody? Give me a sign. Yes, awesome. Thank you so much. All right, good. So let's keep moving. The first thing I'm going to do is define what this facet is, right? And think that a facet in Rn, so I'm generally working in an n-dimensional space, it's an affinely independent set of solutions, which are points on the surface. They need to satisfy the constraint at equality. That is, it's not a less than or equal, because that would be being below the hyperplane. It's being on the hyperplane. So you need to be at equality. And affine independence is slightly different than linear independence, but they're strongly related. And there is a simple way, you can look it up on Wikipedia, that basically says that if I have n points, remember each of the x are n-dimensional thing, right? But if I have n points, they're affinely independent if by adding an extra 1 at the end of the coordinate space, then the corresponding point in the lifted space in Rn plus 1 are linearly independent. And linear independence, just a reminder, it's the idea that if you sum up with a bunch of alpha coefficients all your x's, the only way to get 0 is for all the alphas to be 0. Right? So that's the only way. Otherwise, you could re-express any one of these x's in terms of the others, right? So if you have two vectors like this in 2D, you can express anything that's a combination of these two guys by using two alphas, right? It's the parallelogram rule for vectors. You know that very well. But if I'm basically telling you, no, the only way to get a 0 is that all the alpha must be 0, it means it's impossible to actually express anybody any one of them in terms of the others, right? So and they span the space when we have that. So this is kind of a neat thing. Given this, I'm going to go back first because I need to have real problems. Remember, I'm going to exploit the semantics, so we need to understand the semantics of the problem. So I'm going to take a problem you've already looked at, the warehouse location, just a refresher. In blue on this picture, right, we have our warehouses. They're here and here. Some of them are closed. The blue are the open one. And then the black point are the customers. And my cost is a sum of the fixed cost for opening a warehouse at a site. Here, there are fixed costs here and here. And the black lines is the transportation cost from the customer to the warehouse that's closest to him, because that's how the assignment is made. Okay? So if I do that, I can write a linear program. You've already seen this one. You remember that it's not really that special. Two parts to the objective, the fixed cost, the transportation cost. I'm using a whole bunch of binary variables, whether a warehouse is open or whether a customer is assigned to a specific warehouse. Then I have the fundamental constraint to say that, yay, you know what? You cannot assign a customer to more than one warehouse. That's that one. And then every customer needs to be assigned to some warehouse that happens to be open. So if a customer is open, the corresponding warehouse that it's assigned to needs to be open, right? So this is the basic constraints. Nothing really special. We had already seen that before. Now that we have this in place, let's ask ourselves, what are the facets here? And there might actually be facets already. We don't know, right? So if I look at these equations, I may be asking, do they define facets? And it turns out that actually the simple linear inequalities, YWC less than XW, do define facets. Because if you take endpoints that are a solution to a facet equation, here I'm doing it for customer 1, I'm getting the points in the hyperplane, I'm sticking a 1 at the end, exactly like we have defined here, if you add a 1 at the end, if these guys are linearly independent, that is, if I cannot find alphas that are non-zero that makes the sum equal to 0, if that's the case, then lo and behold, these points are linearly independent. Therefore, the end solution, dropping that guy, are finally independent, and the corresponding constraint is a facet. And if you check this, I would encourage you to check with just 3 points, right? Make a tiny version of this. Check with 3 points, and you'll see that indeed they're linear. These guys, these rows, if you had just 3 of them, they're linearly independent. So we are getting facets here. So this is kind of a neat thing. For warehouse, we're getting facets out the door. Here's a slightly more interesting one. I'm going to look at another problem, which is called node packing. Now, node packing, the idea is to find a subset of maximal cardinality W. So I want the largest subset W of the vertices, such that 2 vertices are in W if and only if they're not connected by an edge in the graph. So if I have this graph, you're probably thinking, hey, where is a node that belongs to a packing? So anybody has a suggestion? I know it's going to be a little bit slower to do that live, but let's try. Can anybody give me like a nice node packing? Maybe not the maximal one, right? But give me one. What would be a node packing on this? 2, 5. Yes, absolutely. Now, what is the rationale? Sage, you're right, it's 2, 5, because 2, 5 are not connected by an edge, and you'd be okay. Now, let's try and add the vertex to 2, 5 to make it bigger even. Can I add 6? The answer is no, right? Why is that? Because the moment you throw in 6, you have the edge 5, 6, prohibited, or you have the edge 6, 2, also prohibited. So I cannot throw in 6, it doesn't work. Right, so this can't be done. We have the same situation if we're trying to add 4 into the mix or 3 into the mix. It's not going to help us. Even 1 into that mix won't help. So yes, they're packing, and we can find a maximal 1, right, which is the name of the game here. And if we look at this, here is an example of a node packing of size 1, and here is another one of size 2. Notice, as Sage pointed out, 6, 4 is not the sole 2 node packing. We have 2, 5, we have 2, 4, we have 5, 3. So there are several of size 2, but there are none of size 3. Everybody sees that? No packing of size 3, you can't do it. Yes? No? I'm sure you're seeing that. It's not going to be that difficult, but this is exploiting your knowledge and understanding of graphs and packing, right? So you can't get a packing of 3. So how do I actually make a mixed integer programming model to compute such a packing, right? That might be an interesting thing to do. So how do I compute that? Well, it turns out it's not all that difficult because you write this program. Now, why does this work? Okay, let's try and understand. I'm basically having a bunch of binary variable, 1 per vertex. Okay, so each vertex has a Boolean variable that's 0, 1. And I'm maximizing the sum of my variable, which means that the variable that are 1 are the one picked in the packing. If I pick 6 of them, then the maximum is 6, right? If all 6 are at 1. But now, for every edge in the graph, I'm going to put a binary constraint that says that because there is an edge between x1 and x2, the sum of x1 and x2 is upper bounded by 1, because if I take x1, x2 must be 0, right? And that's completely consistent with this picture. If I pick 1, because of the edge 1, 2, 2 cannot be in the packing. If I pick 2, 1 cannot be in the packing. So the edge 1, 2 turns into a constraint into the MIP, which is a binary constraint, and we repeat that for every edge in the graph. All together on this one? Pretty clear? I guess. Okay. I think I saw a yes from Sage. Good. Awesome. Thank you. So, if that's the case, then the question is, how well is this going to work, right? And that's an interesting question. How well is this going to do? And the question, if you ask yourself, what is it going to do, is of course, we've asked that question before, is what does the linear relaxation do? So now, step into the shoes of an LP solver and ask yourself, what is the LP relaxation here going to give? So any guess, without looking at the slides, I know that they're online, but yeah, try to tell me. What would the linear relaxation do here? It would pick fractional values, most likely, right? Or maybe not. Maybe these things are facets, and I'm going to get an integer solution. But, you know, it's got to pick values between 0 and 1 for every variable. So, all 0. Okay, Fabio think that we're going to go for all 0. Now, all 0 would do what? Let's go and do them by one by one. So, all 0 would do what? It would basically make every constraint satisfied. So, you're feasible. But then the max is 0 plus 0 plus 0, it's 0. Okay, so it is a feasible solution, all 0. That's good. Gordon is telling us half. Why half? Because if you do half for everybody, x1 plus x2 is 1 half plus 1 half, which is 1, which is less than or equal to 1, and it's obvious to see, therefore, that all the constraints are feasible. But now, every variable being half, since I have 6 variables in the objective, the maximum is 3, much better than 0. So yes, Gordon's right. It's going to pick 1 half for every single variable. That maximizes my objective. And you see how sneaky the LP can be. Because that LP chose something that may feel a little counterintuitive. Picking point half is the easy way out. It's not committing to any integer value, picking the middle of the road for everyone so that you satisfy all the constraints and you make the objective as big as possible, right? The LP always does things like this. 0 was okay because it's a BFS, but we have an objective that maximizes. So the LP will take the easy way out and say, heck, I'm still relaxing all the constraint with 0.5 and I'm out of the woods, right? So I think that everybody probably has seen this. It's a very natural development. Now the question is, what can we do about this? Right, so we're getting a bunch of 1 half. It doesn't give us very much. So what can we do about this? Well, the solution is to say, you know what? My solutions in this graph, they have to satisfy some properties. And yes, 2 vertices connected by an edge cannot appear in a maximal node packing, right? Because they're touching. But it's richer than this. Look at these cliques. Basically, a clique, just to refresh everybody's memory, says that for every pair of vertices in the clique, there is an edge connecting them. So I give you 2 graphs here, the left one and the right one. So let's look at the left one for a second. It has 4 vertices and 5 edges. Is it a clique? Anybody wants to make it a clique? Or if it's not a clique, what would be a clique in that? And maybe it's difficult. What would be the size of a clique in that? What's the largest clique you can get out of the left one? Largest clique on the left one. 3, indeed, right? Because note that the southmost vertex, this guy, and the northmost, they're not connected by an edge. So it doesn't go for them. But this triangle, everybody's connected in it. So that's a clique of size 3. There is another one here, clique of size 3. These 4 were missing an edge to work, which was added in the next picture. So this vertex of size 4 has a clique of size 4. And therefore you know that if you include one of these guys, let's say I include this guy, this one that my mouse is pointing at, I put him in the node packing. What do you conclude about the 3 other guys? I know it's the delay and stuff. I can't ask too many questions. So what's the effect on the 3 other guys if you have the one that my mouse is on in the packing? Anybody? Do tell. Promise, it's not a tricky question. This guy is in the packing. Can you conclude anything about the three other vertices that are above these three guys? Come on, come on. I know some of you know. They can't be in the packing, right? Because they would touch. By definition, since they are in the clique, they all connect to that vertex. So they can't be in the packing. Okay, that's neat, right? Each time you find a clique, you basically exclude a bunch of vertices from the packing by virtue of having a clique. Okay? And this is neat. The bigger the clique, the better the exclusion. Big cliques will rule out a bunch of vertices the moment you pick one from the clique. So going back to the previous graph, right? So this one, here, what's the biggest clique? Do you see a big clique on this graph? Again, it's not a trick question, I promise. What's the biggest clique on that? How many vertices? 3, yes. So if you pick 4, you have a clique here, you have a clique there. So, of course, because of the clique of 3, 1 and 5 cannot be there if you picked 4. But notice that there is another clique here. And because of this clique, when 4 is in the node packing, 1 can be there. We already knew that, but 3 gets pulled out as well. So I've removed everybody in the fringe, which means that the only vertices where I need to make a decision are 6 and 2. And that's how this helps, right? So this is going to be, that's the insight. And you see that this is a property of the graph. I'm looking at the graph and I'm looking at node packing, the semantics of node packing. And I know that any solution, I cannot have 2 vertices that are in the clique in the original graph that are in the solution of node packing, by definition of what a packing is. And that's where the strength comes from, right? This is how we're going to do this. So in general, if I have a maximal clique, that is, it's as big a clique as can get, I cannot push it any further, then if my maximum clique is 5 vertices, it means that the inequality x1 plus x2 plus x5 is also bounded by 1. You can take only one vertex in the clique. And now you have a beautiful algorithm for generating cuts. I give you a graph and you generate me large cliques. You generate me maximal clique. Find all the maximal cliques. For every single one of them, add an inequality. That inequality will eliminate vertices the moment you pick a member of the clique. Does this make sense? Thumbs up is good enough. And then while you're answering that, I'm going to directly ask the next question. How hard is it to find cliques? How hard is this to find cliques? Maximal clique. Anybody? Yeah. It's a mess. Finding cliques is expensive. So now you're shaking your head in disbelief. What is he talking about? He replaced a hard problem, which was solving an IP, by another hard problem, which is finding maximal cliques. That's true, right? I replaced a hard problem by another hard problem. And you're thinking, this is sheer insanity. Is it though? What is the way out? There is one, right? Because if you think about this, when I was looking at the naive formulation, these were also cliques. They were cliques of size 2, right? No, we don't quit. Come on. We don't quit that stuff. That's correct, Gordon. You don't need a maximal clique. The trick is to say, just give me some clique. Each clique I find is going to strengthen my formulation. Sure, granted, if you give me the biggest clique, that's the best strengthening you can get. But any clique will do, and any clique will help. So that's the basic idea here, is that our oracle will be producing cliques, but it doesn't need to get the largest to be correct. Any clique will do. Any clique will help improve. And all I can do is find big ones and start filtering with it. And that's the king side, right? Now notice that in this case, you get a facet when? Only for maximal cliques. The maximal cliques give you facets. So getting facets is sometimes not attainable, right? I'm not saying that every clique gives a facet. Maximal cliques do. But if you're finding other cliques that are a little smaller, you're still getting the benefit from the filtering once you add that constraint as a cut, because it's valid. It's weaker than a facet. It doesn't touch the polyhedron. It's getting closer, but it's helpful and it's worth doing. So that's the basic insight behind this one. All right, so let's look at it. Here is a linear program, all right? And I already threw in a number of inequalities. And you can ask yourself, you know, hey, what is the linear relaxation of that thing, right? So this is the usual argument. Can you give me a linear relaxation for that? So we played that exercise before. I know we could set everybody at 0, right? Because all the variables are Boolean. If we set everybody at 0, then the max is 0, every inequality is satisfied. But what will the LP do is the real question. So remember, the LP is a sneaky, sneaky little boy. What is he gonna do to this? Any suggestion? I'll have my coffee in the meantime. That's a perk of actually lecturing online. I can have my coffee while you work. So what is he gonna do? Ta-da. Set everybody to 1/3. Ah, yes, yes. Okay, let's try Sage's suggestion. 1 over the largest clique size. Ah, good suggestion. So let's try the Sage. It came in first. So 1/3. So basically Sage is saying, look at the first inequality. 3 variable, and I've seen that when we had 2, he was setting everybody to 1/2 to satisfy. Here, by setting everybody to 1/3, we're definitely between 0 and 1. 1/3 plus 1/3 plus 1/3 is 1. It's less than or equal to 1. It works. Oh, but look at that. The next one, 1/3 plus 1/3, no choice. Set this guy to 1/3, we're okay. So every single one, this one, 1, 1, 1. So 1/3, 1/3, 1/3. 1/3, 1/3, 1/3. 1/3, 1/3, 1/3. It works. So if you do that, I have 6 variable, everybody will to 1/3, so it's 6 times 1/3. So the objective is 6/3, which is 2. Not 2/3, just 2. Okay? We're okay? So this is a maximum of 2. Can you do better than that? And the answer is, so I'm sure everybody's okay with that, so just again, give me a sign, right? Usually because I don't have your visual to see if everybody's with me. But you're gonna get 1/3 works. It's gonna give us a solution. I'm not claiming it's maximal, but does it make sense? Make sense? Okay, good. So it makes sense. It turns out though that it's not maximal. If you run the LP, the idea of Sage is the right one, but it's gonna go a little further. It's actually going to do this. It's gonna set x0 to x1 to 0 and everybody else to 1/2. Why does that work? Because once you do that, the first column here disappears, right? Because it's 0. Then you get 1/2 plus 1/2, that's 1. 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 And I had 1/2 here and 1/2 here. That's 1 as well. So every constraint is satisfied. This time in the objective x1 is 0 and I'm left with 5 variables, each contributing 1/2. 5 times 1/2 is 5/2. That's 2.5. It's a little bit better than 2. Does that make sense? This is what you're getting out of this. The linear relaxation, once you're adding things like that, notice that if it was just edges, the constraint would be binary. Here, I put a bunch of cliques of size 3, several cliques of size 3, and automatically my linear relaxation strengthened. Remember what I told you, The name of this game is get a good linear relaxation. If you have cuts that strengthen the linear relaxation, they're a boon. And that's what you are seeing on this illustration, right? So linear relaxation gets better as a result of these cliques of size 3 that were added into the mix. All good? I assume. Okay, we're moving at a good clip. Yep, okay, good. And if you have anything, just don't hesitate to ask, right? I'm always looking on the two things. So I'm back to another problem, this wonderful problem of coloring that I'll put into the European setting, right? So France is blue, Belgium is black, like my soul. Luxembourg is yellow, the Netherlands yellow, Germany red, and Denmark up there is in black as well, okay? Now, why am I bringing this up? Because we have a model for this, right? And if you remember the model, it's not that big a deal. It's this beast where I am minimizing the objective, that is the color, the number of colors I'm assigning, subject to obj, the number of colors, is greater or equal to the sum over every color name, V, multiplied by the Boolean that says whether a country C has been assigned to that color. So if color 2, 3 has been assigned, then this Boolean will be 1 times, if V is 3, then 3, 1 times 3 is 3, and therefore I'm basically picking up that as my maximum since it's a lower bound on the objective, okay? We have seen that model before, it's nothing special. Remember, you have the constraint, you cannot have 2 colors assigned to a country, so for every country, the sum of the colors is 1. And then I have the adjacency, right? So on the map, if I take it here, France, Belgium, they're neighbors, right? So there is an edge connecting them, and in coloring, you cannot have the 2 endpoints of an edge assigned the same color, right? It's a classic thing. So if they cannot be assigned the same color, the sum of these 2 guys is less than or equal to 1 for every pair of countries that belongs to the edge set and for every color, okay? So I'm basically prohibiting the same color for these 2 guys for every single color. Good, that's a model. Now I'm going to actually play a trick. I'm going to move this a little bit so that you see it. You see that this gives me an objective of 0.5 because color C0 and color C1 are both 0.5. Again, the LP is doing that funny relaxation, right? Because it's a way to satisfy the constraint that you have here. I only showed that specific constraint. So it's got to put it at 0.5. And therefore, since they're both 0.5, I'm going to actually propagate through this constraint above, up to this constraint above. Sorry, I wasn't pointing at the right place. It's going to propagate to this and tell me that the objective is 0.5, right? So this is the basic ID, because I'm going to pick up half of the color 0 and half of the color 1. And since color 1 is 1, half of 1 is 0.5, so I'm getting 0.5, right? So this is the classic thing. So that's the picture we get. That gives me a proof of optimality for the coloring in, or getting the optimum in 9 nodes and proving it optimal in 41 nodes. Where I say nodes are the nodes of the branch and bound tree. Okay, so that's a solution. Clearly here, we haven't been talking about any cuts yet, right? This is the vanilla formulation of coloring. Now we've been playing with these cliques and these node cover, so we can ask ourselves, is there a way to do better than this? Now back to the map. If you look at this map, you really realize one thing, is that there is a graph underneath that, right? We already said that, and that graph is this. So I'm stylizing now, and you see that in this graph, I have an edge between every 2 countries that share a border. Okay, so Luxembourg touches France touches Germany, touches Belgium. So the yellow point of Luxembourg that you see here is connected 3 ways, to Belgium, to France, to Germany. Belgium and Holland have one edge in common. Notice that for the France, it's adjacent to Belgium, to Luxembourg, and to Germany. So it shouldn't be that shocking. And when you look at that graph, what do you see, my friends? Well, you see similar construct we've seen before. Look at that beautiful little triangle, right? We have a triangle here. That's what the black arrow is supposed to show me. And what does the triangle tell? And by triangle, I mean the three vertices are connected to one another. What does that tell you in terms of your coloring? And it's not the only triangle, mind you, right? There are others. For example, you have Luxembourg, Belgium, Germany. That's another triangle. Belgium, Holland, Germany is a triangle. France, Luxembourg, Belgium is a triangle. France, Luxembourg, Germany is a triangle, right? Heck, France, Belgium, Germany is a triangle. Correct. It's a clique. And in order to have a valid coloring in a clique, every vertices in the clique must have distinct colors. That's a beautiful insight, isn't it? The moment you realize this, you can get a better formulation than this stinking one. Look at this, the constraints are binary. They're only about the edges, whereas this picture clearly tells you there are stronger structure in there. They're cliques that basically further constrains groups of variable. Now the variable corresponding to Belgium, Germany and Luxembourg, because they're all adjacent and form a clique of 3, all these guys must be assigned different colors. So my binary edge can be strengthened to a clique. It's the same trick. I can use a clique from that graph. I can find all the clique, because the graph is small enough here. I can find all the clique and add them to my formulation to get something better. And that's the key insight on this one, right? Now, before, if you recall, with an objective of 0.5 on the naive model, I could actually solve this with 2 colors, right? Because 0.5, you need 2 colors. You need the 0 color and the 1 color. You take the ceiling of the objective, right? So that's good. Now, if I add the 3 cliques, which looks like this, right? It's now basically saying, hey, if I'm summing over the vertices in a clique, 0, 3, 4, so that's one of those cliques, if I sum over the colors, then the sum of V times the color is at least 3, right? Once I do that, I solve the LP. It's becoming difficult to predict exactly what the LP will do. But if you solve the LP, you'll realize, hey, nothing changes. My optimal is 9 node. I get still 41 node to prove it. And my objective though, at the first solution, it jumped from 0.5 to 1.0. But since I was taking the ceiling, I already knew it was 2 colors. So it's still 2 colors. So even though the linear relaxation has strengthened, it hasn't strengthened to the point of actually giving us a lift. But there was a strengthening. So the cliques did help. Now you can actually push that one notch further and recognize that, hey, what about adding the 4 clique? Because if you look on the picture, such a thing exists, right? And if you do that, then you end up with an objective of 1.5 that tells you, no, my friend, on that map, you need 3 colors. And once you need 3 colors, the effect is immediate. And again, I'm going to move the picture so you can see. I get my optimum in 5 nodes rather than 9, and I prove optimality in 9 nodes. So it's a substantial reduction of the search effort in the branch and bound simply because I had a strong enough bound. And in case you forgot, right, the 4 clique, we can go back and take a look. Where is the 4 clique? Can we find the 4 clique? Sure, I can do that. By the way, the 4 clique here is the thing in red, right? Dashed red, because the blue is connected to all 3. The yellow is connected to the black, the blue, and the red. The red is connected to the black, the yellow, and the blue, right? So everybody is connected to everybody. So this is a 4 clique. That's the 4 clique I was talking about. Now, why does this work at 1.5? This one, so you would see it. I didn't compute it by hand, right? But once you had this inequality and you solve the linear program at the root node, the first linear bound that comes back from the linear relaxation will tell you 1.5. Since you need a number, so this is telling you need 1.5 color. And I say 1.5, it's the index of the last color, right? If you look at the model, so this 1.5 is really the index of the highest number color in the model, because I'm minimizing that, and this is bounded by this value. So it's the index of the higher numbered color. So you need index 0, you need index 1, but since you need 1.5, the only thing you can do is go up. You need index 2. So you need index 0, index 1, index 2. That's 3 colors. That answers your question, Gordon? So these are the indices. That's why. You need color 0, color 1, color 2. So when you have a 1.5, you need 3 colors. Good. All right. So I think that makes it clear that once again, the cliques are a blessing. With the clique, we can actually get a better solution. All right. So we've done this. You see that it has an impact on my branch and bound. Again, oh, that doesn't help, does it? I stay put. See, I forget that there are certain things I can do, but 9 nodes for the optimality proof rather than 41. So a substantial savings once we do this. All right. With that wraps up the first part. Now, in the last lecture on the MIP, I'm really going to start pushing and looking at other kind of cuts, and we have the time, so I'm going to switch now to the next deck. So, hang on. Cheap, look at that. And here we go. So again, right, so same thing. We're now into the next one. We're going to look at a few more cuts. And in particular, we're going to look at cover cuts and then finally TSP, okay? Good. All right, so what are these cover cuts? It's another kind of cut that is structural. It uses semantics of the problem, just like we used cliques for node cover as well as coloring. This is another kind, and we're going to see what they represent. They arise when you have constraints of the form above, right? So when you have a constraint like the one above, right, that thing, the sum of the aj, xj less than or equal to b, you can ask yourself, are there facets that correspond to this? And the answer is yes, they are, if you think about this carefully. So I'm going to define first what a cover is. A cover is a subset of the indices of the variable showing up in such a linear inequality that satisfy a specific requirement. So it's a subset C of indices from these are the indices of the variable. So I go 1 through n, right? This is the sum is 1 through n. These are the indices of the variable, okay? And I'm saying it's a cover if the sum of the aj for all these indices exceeds b. So I'm adding the coefficient, and I'm saying if you add up the coefficient of the variable whose indices are in the set C, you should pass b. If that's the case, that set C is a cover, which basically means that if you were to include, by setting the corresponding variable x to 1, if you were to include all the variable in the cover, the inequality above, this one, would be violated. So you are a cover if picking all the variables in the cover would break the linear inequality above. Furthermore, I'm going to talk about a minimal cover. And a minimal cover is easy to understand. A cover is minimal if, when you drop anybody in the cover, it loses its covering property. Meaning, if I drop a single index out of this set, then I can take everybody else, and it still satisfies this inequality, right? So the cover is, in a sense, the smallest subset of indices, such that if I take everybody in it, I will break the linear inequality above. If you drop any single one, it's satisfied. That's a minimal cover. Are we happy with this definition? Everybody's with me? Yes? No? Give me a sign. Coffee in the meantime. It's exhausting. maybe, possibly. Come on. Sign. I know that's a 10 seconds delay. I'm not very patient, am I? All right. Yep, Gordon's with me. Okay. Thank you, Gordon. So I'll go on and look at what this means, right? Well, yes, but this is not the objective, the constraint above, right, Sage? So this is a linear inequality that defines a half plane for my polyhedron, right? So I didn't even talk about the objective function. The only thing here is that I have a half plane. I'm saying I'm taking the space below. That half plane is given by this inequality. And I'm basically saying in this inequality, there is a subset, and we're going to look at an example in a second. We're looking at a subset of the terms such that if you include all of them, you blow past B. That's what this means. This inequality here kind of assumes that all the x's in the set C are taken. They're all 1. If I take everybody in the set, I blow past C. If the cover is minimal, dropping 1 is enough to restore feasibility. So I'm really at the edge of feasibility. The cover is saying it's an object that's close to that inequality and that half space, but hopefully it's going to be tighter. And we're going to see why it's going to be tighter in a second. All right? So I hope that answers your question, Sage. With that, I'm going to start, and if it's not, please ask again, right? I'll be looking in the chat. If not, let's take a look at an actual example to try and make sense out of this. So if I have that, I'm going to say, cool. Let's say that I have a cover C, which is a subset, and it's a cover. So it has the property that if you include everybody, you shoot past B. So I'm saying I'm going to manufacture a brand new inequality, and that's the one you see here. And that brand new inequality is basically saying if you take everybody in the cover C, or if you count the number of people you take in the cover, because the x are Boolean variable, you take the vertex or you don't, right? So it's a 0, 1. So if you take everybody in the cover, if these x are true, this sum cannot reach the size of a cover. It cannot reach C. Because if it did, well, by definition, I would be blowing past B. The sum of the coefficient would be blowing past B. So if I include everybody, the sum of the coefficient blows past B, therefore this inequality is invalid. So I'm basically saying a valid inequality is to say, yeah, you gotta be 1 below the size C for the variable that appear. And this is a valid inequality. And it's better than the original one. Remember, the original wasn't there. That was my original. This looks similar, but it's stronger. And why is it stronger? First, here, we were using all the terms. Here, we're using a subset of them. Here, we were scaling the variable by coefficients. Here, the coefficients have disappeared. We're just counting the variables that are included, that are 1. And then I'm bounding by the size of the cover, because I know that if I get past the size of the cover, or if I get at the size of the cover, I will be, the sum of the coefficient will be greater than B. But it's a slightly stronger statement. It's a valid inequality that allows this to work. Now, let's look at a numerical example. Look at this beautiful linear inequality above. And of course, to make things easy, I've sorted the variable by the coefficient. So the largest coefficient is in the front, 11, 6, 6, 5, 5, 4, 1, right? This cannot exceed 19. And I'm basically saying these two things underneath are minimal cover inequality. Now, can you see why? Right? This is the one thing, I didn't show the development, but I gave you the theory before. So what's a cover? It's a subset of the terms from this linear inequality that basically, or even the minimal cover, it's a subset of the term in this inequality which, when added, shoot past the limit 19. Since they are sorted by coefficient, let's see what it is. If I include x1, I would pick up 11 units. I include x2, I would include 6 units. So 11 plus 6 is 17. These two alone do not get past 19. They're 7. These two are 17. If I add x3, what's happening? Well, 17 plus 6, it's 23. That's past 19. Drop any one of these three. If I drop these three, drop anybody. You drop x3, your sum is 17. You drop x2, your sum is 17. You drop x1, your sum is 12. So all are, if they are dropped, they would make the inequality feasible. So this, the indices 1, 2, 3, form a minimal cover. And you know the requirement. The inequality is the sum of the Boolean variables that are in the cover has to be less than or equal the size of the cover minus 1. Since there are 3 variables, size of the cover is 3, size of the cover minus 1 is therefore 2, so x1 plus x2 plus x3 is 2. Make sense? Give me a sign. And while you're making a sign, you can reason why this is also correct. Right? So 3, 4, 5, 6, you can place that game. 3, 4, 5, 6, let me highlight them so that you see them. It's these guys, right? So it's 6 plus 5 plus 5 plus 4, so that's 20. 20 exceeds 19. Drop anybody, you drop below 19, or less than or equal to 19, so this is another minimal cover. If it's another minimal cover, the sum of the Boolean variable for the minimum cover, less than or equal the size of the cover, 4 minus 1, 3. That's another valid inequality. All right? So it's pretty clean once you see that. Cool. Now, can we do better than this? And the answer is yes. If you have a minimal cover, it turns out that I can enlarge the cover. I can actually add more terms into the sum without changing this. Remember, the right-hand side is the size of the minimal cover. So I'm going to use the size of the minimal cover minus 1, but then I'm going to take my minimal cover and I'm going to extend it. And the extension definition is here. What is the extension of my minimal cover C? It's basically the set of indices for which the coefficient is larger than a coefficient that's in the cover already. And again, you can ask yourself, why does this work, right? So now I'm basically saying, let's get a minimal cover. I'll use its size, but now my minimal cover, I'm going to make it bigger and include more terms. And if I include more terms, it's going to work. It's still going to be a valid inequality for the same expression I had at the beginning. Now, let's look at the example. This one, 3, 4, 5, 6. Look at that, 3, 4, 5, 6. I'm basically saying there is a stronger cover inequality. And what is that? Well, I'm going to use the same tree here. That will be this one. But you notice that I'm adding terms. I'm keeping 3, 4, 5, 6, but apparently I'm adding 1 and 2 as well. Why? Because 1 and 2, their coefficients are larger than the coefficients in here. So therefore, they also would help you blow past the value. So adding them in makes this side of the inequality larger, while this right-hand side does not change. So it's a tighter cover cut. Does this make sense for everyone? These cover cuts are pretty nice. They, both the basic one and the extended one, they allow us to add mechanically by thinking about the semantics of the problem. They allow us to actually add additional inequality that strengthen. Say exactly like for the clique, find as many as you can, right? So how do you choose? You can do what I've done. You sort the coefficients in increasing order, and then you do a linear scan. You keep including the coefficients until you get blown past. When you're here, you blow past. So if you blow past, okay, that's a minimal cover. How do you find the next one? Drop the first term. Drop the first term, you have this, and then you resume adding. So you're 12, 17, you add a 5, 17 and 5, ba-boom, 22, you passed. That's another minimal cover. Notice that here, drop anybody, and you're less than or equalities, right? So you realize that there are a lot of these cover cuts. Does that make sense? Because you can move the window over a single inequality, and then you can get all the extended cover for those. And then you can do that for every single linear inequality in your problem. All with me? Hope so. So this is not too bad to actually get them. All right. Awesome. So now that we have this, you see what branch and cut becomes at this point. It's a game that basically says, I have an application. I'm going to first come up with a linear formulation and express that as a MIP. I need to have a linear objective. I need to have linear inequalities and equalities for my equations. I can solve my linear relaxation. If it happens to deliver a vertex whose coordinates are integral, I'm done, because that's optimal by definition of the simplex, right? If that is not the case, then we can say, look, I could branch, but branch is a move for disparate men. And we're not going to do that first. Our first move will be, let's try to obtain cuts. And the first flavor of cut you can get are polyhedral cuts. Why? Because the polyhedral cuts correspond to things that are closer to facets. And if they deliver facets, your LP is much more likely to give you a point whose coordinates are integral. If that's the case, you stop. So you maximize the chances by taking polyhedral cut that when you go back up and solve the linear relaxation, you'll be integral and you stop, right? So find a polyhedral cut that prunes the linear relaxation. It's a facet if possible. We've noticed already that it's not always a facet, right? When you're picking clique, if the clique is not maximal, you're not necessarily getting a facet. You're getting a cut, but it's not necessarily a facet. If you can find such a thing, you do it. When you run out of option in your polyhedral cut, and right now in your tool chest, you have a couple of them. You have the clique cut, you have the color cut, you have the cover cut. We'll see another one very soon, but you have a handful. Remember that real solvers have about at least 100 of those under their belt they can apply. If you don't find any, use Gomori cuts. They're syntactic and they also cut the basic feasible solution. So you can apply Gomori cut until you're blue in the face or the objective does not improve enough. When you're totally and utterly desperate, you switch to step 4, which is, look man, I can't get a solution, so my only option is to say, I'm gonna branch. That is, you're gonna pick a variable, split it in half, or, oh, you can't hear me? Okay, the others, can you type? Okay, so then I guess it's a problem on your side. And with the name, I don't know who you are. Yeah, I'm gonna give you a second. Try to reload like Sage suggests. Seems to be a client-side issue. Or maybe battery in your headset, or I don't know. I'll give it a second. We have time. Haha, coffee for me. Okay, so you're back in business? Sounds like you are. So as I was saying, right, so yeah, the basic idea is use this polyhedral cut, then use the Gomori cut when, okay, great. If this actually gets you to an integral vertex, you're done. If not, then you despair, you shake your head in disbelief, and you fall back to your only option. You branch, right? And you're gonna branch and add, create two sub-problems by adding inequalities that says that a specific variable that is fractional should be less than or equal to the floor of a fractional value or greater or equal to the ceiling of a fractional value. Yes, they do. The MIP do, Gurobi, Cplex, all the big boys, they actually do automatically the click and the cover cuts. As I said, they have about 100 different ones in their arsenal that they can tap, right? They can come up with cuts automatically for your problem, and they try to be smart and recognize. They will look at your inequalities. For example, a thing that Gurobi and Cplex do, if they see a lot of binary inequalities, like edges, and they see a bunch of edges, they'll say, this thing must encode a graph. If it encodes a graph because there are lots of linear inequality, I'm going to try to assume, let's look at the subset of these binary inequalities that are encoding edges, and I'm going to apply a click discovery to that. And that's always correct. So yes, they do auto-detect them, and they try to be smart because it takes time, right? Coming up with these cuts, as you understand, if you're looking for max click, that's a hard thing. So they do best effort. They try to auto-detect. They try to be smart to actually look for the right kind of cuts to compute and then add. They may, on a single iteration of the simplex algorithm, add maybe 20 cuts all in one go and then re-optimize. It's not like add a cut, re-optimize. They batch them as well. So they're trying to be pretty smart about this whole business of adding cuts. All right. So we understand the idea, right? Now the branch and cut is basically linear relaxation. You go to the library of cuts. You try and apply the ones that seem sensible. You generate cuts. You add them. If you get a non-fractional solution, you're done, right? If your solution is integer. Otherwise, you keep generating. When you're desperate with the generation or nothing works, then you fall back on branching. Right? Branching is the move of desperation. So this brings me to a fundamental thing, is that how does a MIP solver do that, right? Because if you're looking at a solution of your linear relaxation, X star, you can enhance it with cuts. And we'd like to find out whether there exists a cover cut that actually knocks off that solution, right? That's typically the question we're going to be asking. And it turns out that you can do that. That is, because here I just described cuts in general. I didn't say cuts that cut the BFS. Now I'm focusing on, yeah, sure, but I don't want any cover cut. I want a cover cut that is violated by the current BFS, right? So that's the main point. And if you look at it, it's not too bad because the cover inequality, and that's the one I'm going to use, the cover inequality for my linear sum of aj, xj less than b, it was that. So that was my cover cut, right? So everything in the cover has to be, if it's included, the sum of the guys you include has to be less than the size of the cover minus 1. That's great. So you realize that I can rewrite that into the next inequality, right? Everybody sees that? So what is the game here? Is that I'm basically taking my C's, right? So this is the size of C, and I'm moving them to the other side, and then distributing, since there are C terms in my sum, I'm going to distribute this quantity C, a value of 1 to each term. So because it was C, it becomes minus C. So the minus C is a bunch of minus 1, minus 1, minus 1, minus 1. I group each of the minus 1 is with xj. And then, of course, because I'm dividing by minus 1, I'm changing the direction of the inequality. And therefore, that becomes 1 minus xj rather than xj minus 1. And now I have to be greater or equal to 1, right? So these two are exactly the same. I imagine everybody's happy with that. Because they're exactly the same, the question of, does there exist a cover that basically satisfies this condition, that is the negation of the above, and for which the sum of the aj is greater or equal to b. If I can find such a thing, I have found a cover cut that basically would violate the solution. Why is that? Because I can basically say, look now, I'm going to use this requirement. So this gives me a requirement, right? I want a cut that looks like this, and it has to satisfy that requirement to cut the solution. So I'm going to say I have to choose a bunch of z's such that if I take the corresponding a, I'm greater or equal to b, which is exactly this inequality. So I'm looking for something that satisfies that. And what do I want? I want to minimize a sum of 1 minus xj star. I'm using the current solution of my LP. This is this thing. And I'm multiplying that thing by the z's. That is, I'm deciding which one to include. If I find such an object, that is, if the minimum value that I find is lower than 1, then this is lower than 1. And therefore, it's lower than 1, and therefore it satisfies this requirement. So it's a valid cover cut. Right? So this is the problem I have to solve. Can't select correctly. This is the problem I have to solve in order to find a cover cut that blocks off the current optimal solution, which is x star. And you look at this, and remember, the x star j are fixed. They're constant because they are the current solution to the LP. You solve the LP, you stopped on the BFS, which is fractional. You picked up the x star from it, then you formulate this thing. Plugging in the x star j is constant. So you end up having 1 minus a constant times zj plus 1 minus another constant times another zj, etc. Subject to the sum of the aj zj's to be greater than b because you gotta have a cut. And your zj are binary. You include or you do not include the thing. Does that make sense? So solving this problem, if I find the z, I found the specification of a cover cut that cuts the BFS. It's not any cover cut. It's a cover cut I care about because it gets rid of the BFS, and therefore the linear relaxation, when I solve in the dual, will actually restore feasibility and sync. Are you with me on that one? Just on how I derived that program. Yes? No? Again, I'll give you 10 seconds. Oh, no. Mostly, okay? So the thing is, look at the previous slide, right? Yeah, this is the specification of my cover cut. I want that. I'm rewriting it as this. I haven't changed anything. So this is the same cover cut. What I'm basically telling you is that to get the cover cut, I need to find C. So my problem is compute C. But I don't want any C. I want a C that kills the BFS that the linear relaxation gave me. And I'm basically saying, okay, so I want to find something that's a cover cut. So it has to satisfy this requirement, therefore violate the inequality above, because that's what makes it a cover cut. And it needs to look like this so that I actually get my cut. The way I do it is by expressing this thing. And now, of course, that's how I end this lecture, or this point, is that this thing that you're looking at, you know what it is. It's an IP. Yes, you're minimizing a sum of coefficient, these guys are coefficient, multiplied by Boolean variable, subject to, and you're minimizing it, subject to linear inequalities. So in order to find a cover cut, I solve another IP, a completely different one. But that IP, if it terminates with a value less than 1 for the objective function, I definitely know that I have a cover cut that I can add into my original IP. So in order to get the cover cut, I solve a nested IP problem. That's how it's done. And you realize, just like finding the maximum click might have been expensive, I'm solving another NP-hard problem here, but that NP-hard problem, I frame it as an IP itself. So I solve an IP to get the cut that I add into the original IP just for the sake of trying not to branch and having a polyhedral cut to be added into the mix. That's it. That's where I want to stop today because it's 12:15, 16 even. So I've covered all the important bits. Please review that as you play with it. As you know, we are 1 week out from the previous homework, so I'll start looking tomorrow at what you have produced for me, and I will post on the website your next assignment, which is solving LPs by hand, right? With that, thank you so much. I hope this was useful. Hopefully there won't be snow on Thursday, though I'm afraid that when I looked at the weather this morning, the forecast for next week calls for another storm on Tuesday. With that, see you next time. Bye-bye.
Yeah, we'll meet again. I don't know where, and I don't know when, but I do know that we'll meet again some sunny day. So honey, keep on smiling through, just like you always do, till the blue skies drive all the dark clouds far away. And will you please say hello to all the folks that I know and tell them that I won't be long. They'll be happy to know that as you saw me go, I was singing this song.
We'll meet again. Don't know where, don't know when, but I know we'll meet again some sunny day.